Alright everyone, and welcome to the AI Research Roundup. I am your host, Alex. Today, from the Papers with Code trending list, we have Impromptu VLA, Open Weights and Open Data for Driving Vision Language Action Models, published May 29, 2025. Its core contribution is the Impromptu VLA dataset. That's over 80,000 video clips from 8 open-source datasets, focusing on corner case scenarios. These corner cases are tricky, unusual road situations for self-driving cars. The paper uses Vision Language Action Models, or VLAs. These are AI systems connecting vision, language, and driving actions. Importantly, Vision Language Action Models, trained with this new Impromptu VLA dataset, show significant performance gains on benchmarks, helped by its rich annotations. And speaking of making this research accessible, the authors also shared their implementation on GitHub. So in their Impromptu VLA repository, you'll find the code for data Q&A generation, model training, and inference. That's how the model makes its decisions. Plus, they've included pre-trained models and the new scenes data files, which is fantastic for anyone looking to dive in and build on this work. Okay, so Figure 1 really brings this Impromptu VLA dataset to life. You see examples of those tricky corner cases we discussed, like roads with unclear boundaries or unexpected obstacles. The central diagram shows the 80,000 clips supporting various vision language action tasks, such as scene understanding, vulnerable road user identification, and motion prediction. And importantly, on the right, the bar charts show clear performance improvements. For example, the Neuro NCAP score, a benchmark for AI driving safety, is significantly higher. Also, the trajectory prediction L2 error, which measures how accurately the AI predicts a vehicle's path, is lower, indicating better predictions. So Figure 2 broadens our view by comparing characteristics across different driving scene datasets. Part A, on the left, illustrates the category distribution. So how frequently different scene types like unconventional dynamic obstacles or roads with unclear boundaries appear in various datasets. Next to it, the bar chart shows the clip count, giving a sense of scale. Then Part B is quite telling. It compares trajectory distributions. Trajectories are the paths vehicles follow, and their distribution shows the variety of these paths. The plot labeled Hours highlights the diverse trajectories within the Impromptu VLA dataset. Finally, Part C displays example images from the 8 source datasets, categorized by these tricky driving scenarios. Alright, so Table 1 gives us a more detailed breakdown of these 8 source datasets that contribute to the Impromptu VLA dataset. It lists key attributes for each, like the number of camera views, image resolutions, and FPS, or frames per second. Frames per second is a measure of how many distinct images are captured each second, which contributes to the video's smoothness and detail. Looking at the totals, the sum column shows these 8 datasets provided an initial pool of 2 million raw video clips, a massive 10 terabytes of data. From this, the 80,000 labeled clips for the Impromptu VLA dataset were curated. Now, Figure 3 illustrates the entire data processing and annotation pipeline. Basically how they went from that raw data we just talked about to the final, curated Impromptu VLA dataset. It starts with dataset collection, which we've covered. Then, Step 2 is creating a taxonomy of unstructured scenarios, which means classifying those tricky driving situations. Next, there's frequency alignment, where they adjust the video's frames per second, for example, from 10 Hz down to 2 Hz, ensuring consistency. After that, they perform clip selection, picking out the most relevant video segments. So, after all that careful data processing we just discussed for Figure 3, Table 2 demonstrates the tangible impact of this work. This table focuses on the Neuro NCAP benchmark. Remember, that's an important AI driving safety score. We see a comparison of different models, looking at their Neuro NCAP scores, where higher is better, and their collision rates, where lower is definitely preferred. The key finding is that when the base model is trained with the Impromptu VLA dataset plus new scenes, it achieves a notably higher average Neuro NCAP score of 2.15 and a lower average collision rate of 65.5%. These improved scores suggests the dataset helps models better understand complex road situations, leading to safer driving. Okay, so building on those safety improvements, Table 3 now focuses on open-loop trajectory prediction. This is about how well a model can predict a vehicle's future path without any real-time corrections. The table shows the L2 error for this, measured in meters on the new scenes dataset. L2 error essentially quantifies how far off the model's predicted vehicle path is from the actual path. So a lower number means a more accurate prediction. We see various models compared, but looking at ours and key competitors, when the base model is combined with Impromptu VLA and new scenes, it achieves some of the lowest average errors, around 0.29 or 0.30 meters. This really reinforces that the dataset helps models make better, more precise predictions about future vehicle movements. Alright, so Figure 4 provides a really clear visual of what those improved NeuroNCAP scores and lower collision rates actually look like in practice. We see side-by-side comparisons of driving behavior in challenging scenarios, specifically static, frontal, and side encounters. In each pair of images, the left shows the base model, which is fine-tuned only on new scenes, often resulting in a crash. The right image shows the model trained with the Impromptu VLA dataset and new scenes, and in these cases, the vehicle successfully navigates the hazard, for instance by turning or slowing down. It's a compelling demonstration of the dataset's impact on real-world driving decisions. Those visual examples in Figure 4 really drive home the point. The Impromptu VLA dataset and the open-source model clearly lead to much safer driving decisions and more accurate path predictions, as we saw with the improved NeuroNCAP scores and reduced collision rates. This work is a significant contribution towards more reliable autonomous vehicles by providing valuable open resources to the community. That's all for this AI Research Roundup. Thanks for tuning in. I'm Alex.